On this episode of Far Out, a NASA center known for pushing the boundaries of flight is now pioneering sailing in space.
So light actually pushes it.
And building robots that can creep and crawl around the moon.
Whoa! You think you know NASA? Well, think again. I'm Megan Cruz. Come with me to experience the extraordinary, the unexpected. This is Far Out.
Trivia time. There are NASA centers across the country. Can you name which opened first? Here's a hint. It's in Virginia, and an award-winning film featured some of its hidden heroes who helped get us to the moon. If you guessed NASA's Langley Research Center, you are correct. And way back in 1917, just a few years after the Wright brothers' historic flight at Kitty Hawk, Langley opened as the nation's first civilian facility focused on advancing human aviation. But nowadays, Langley isn't limited to aeronautical research. People here do all sorts of cool stuff, like Jim Nealon, who's designing and building soft robots. Let's see if we can chat with him.
Jim.
Hey, Megan.
Oh, hey, Jim. Did you want me to come down, or are you coming up?
Grab a hard hat and come on down.
Okay.
It's one small step for man, one giant leap for mankind.
Megan, welcome to the surface of the moon.
I appreciate it. It was so easy. I just went down a ladder.
We do it every day.
Because this here is why Jim and his team are making soft robots. NASA wants to learn how to live and work on the moon as a stepping stone to Mars.
So traditional robots that we design are designed with a specific task in mind. When we go further and stay longer out in the solar system, we need systems that will be able to adapt to an unknown environment and be able to maintain and operate within that environment.
Okay.
Soft robots give us that ability to do that. They can form around strange unknown objects and be able to manipulate them or move around them a lot better than a traditional robot would be able to.
And because soft robots, made mostly of silicone, are soft.
If there are astronauts around these robots and they come in contact with the astronaut or the spacesuit, there's no damage there, so they're safe for people to operate around.
I want to see these soft robots in action. So we leave the moon and head to...
Our lab space is right over here.
Okay.
These are all the different types of soft robots we are currently looking at for possible use in space. We have a chainmail like this embedded in the silicon, right?
Yeah.
And you can see in one orientation, it's very easy to roll around.
Okay.
And the other, it locks and can take pressure or force.
This kind of reminds me of that claw you see in the carnival game where you're trying to pick up a stuffed animal.
Absolutely. But those claws are very rigid and they're not
Right.
specifically designed to pick up all of the objects that are in those games.
Yeah.
So a soft robot, however, is very compliant and able to bend around the shape naturally and provide a better grasp.
So this is kind of how we were talking about there might be some benefits to using soft robots versus traditional hard robots.
That's correct. We can take an object like this, a pair of glasses, and if you want to hold that right there, hold it from the top,
Okay.
and I'll apply the air pressure.
Oh, whoa. So because this is soft, like what does it allow this to do better?
It can move into the different areas of the object that you're picking up and provide more surface contact for a better grasp.
Okay. I wish we had a stuffed animal to like actually test your theory, this analogy that we've...
I can help you.
Okay, we do. We have a stuffed animal. Whoa! Look at all the stuffed animals I could have won in all those years, all the money I wasted. What does this one do?
Oh, this is a very interesting new project that we're looking at that's been biologically inspired from the octopus. One of the hard things about building large structures in space is being able to outfit them with power, data, cryogenic lines. A robot like that, controlled like an octopus arm, could very easily go through the structure and place specific cables or data lines in certain areas that a traditional robot would find very challenging to reach. This is very early development. We're just learning the science behind how those octopus tentacles operate.
Learning not just from Mother Nature, but also other soft robots already in use here on Earth. As they say, necessity is the mother of invention.
There's a number of areas right now where soft robots are being used. Search and rescue is one of them, where these soft, pliable robots can get underneath rubble and go search for survivors. Marine biologists use them to collect delicate deep-sea creatures. Also in physical therapy, where it's helping folks regain the use of their muscles and limbs after an accident or an injury. That versatility kind of guides us to the designs that we are looking to have them used in space.
Are soft robotics, is this just a very new field in general?
Soft robots actually has been around for quite a long time.
Since the 1950s, actually, but possibly using them in space, that is very new, thanks to recent advancements in material sciences. By now, you get why soft robots would be an asset for us on the moon. So, do you want to make one with us? We're gonna make this gripper.
In this particular one, which is a gripper, we've actually embedded other fibers in it so that we can do a specific in-space assembly task.
There you go.
And then this is our silicone. So we mix the silicone as a two-part silicone that we'll mix in this cup right here.
Okay.
So you can open up the first one and dump the entire contents into that.
It says stir well before using. Should I?
Give it a good shake, yeah.
Who wants a cocktail? Okay, this one. Shake this one too. All right, so then just open it up?
Open it up and pour them both in.
Okay.
Yeah.
Is it, so I'm assuming that these are different.
Right, this is a two-part compound. What'll happen is when they mix, they'll start to cure and then harden.
I feel like I'm trying to make meringue, you know, with like egg whites. It's our cooking show. It's Jim and Megan's cooking show.
Though I wouldn't want to eat it. Though it's safe.
I think I mixed it pretty well. Keep mixing it. Okay. But what if my arm starts to hurt?
Then switch to your other arm. So now you can stop. Yep. Let's put that spoon down.
Okay. Now pour it into the
And
here?
now pour it into this
Anywhere?
mold right there. Yep. Start, you know, kind of just move it around.
Is it okay that it's going over?
Yep.
Okay.
That's fine.
Oh, I'm so sorry.
That's okay. Yep. Fill it up to the top. Okay. Excellent.
I didn't make too much of a mess. That's good.
No, that's okay. Pick that up.
Okay. Oh my
and
God.
And we'll move it over here.
Oh my God. And this is where it gets messy, guys. All right. Oh, it's so slimy. Oh, that's
Right up
not
on
the
the
right
top of
place to put it. Okay. All right.
There you are. Now, if there's a switch on the back of the pump here, you
Okay.
turn that
Turn
on.
it on. Switch.
And then you close off the valve.
What is this doing?
This closes the valve, so now it's sucking all the air out of this structure, this dome right here, and degassing the silicone.
Why is it important to get the bubbles out?
If we don't get all the bubbles out, there'll be bubbles all through the mold, and it's easy to tear and break when we inflate it.
While we wait, let's find out how we'll make the gripper grip. Jim says we can use computers, but that would mean a lot of additional equipment. Instead,
Another way, going back to biologically inspired systems, is to use an artificial muscle.
So that's going to work like our muscles, like we have in our body,
Yes.
to move the soft robot.
Absolutely.
Wow, that's amazing.
It'll contract and be able to pull the gripper closed, open and closed.
Okay, so we're going to make that muscle,
That's correct. We'll make the muscle.
not make muscles like this. Okay, I have got a lab coat. We're at a different lab, and we're going to make a muscle. So where do we start?
This is a spool of carbon fiber that we'll take a couple strands out of
Okay.
to start making our muscle.
we're using carbon fiber for its strength and durability. It holds a lot of weight and can maintain those heavy loads. We measure out the fiber strands, then add metal ends.
I don't even think I'm doing anything, actually.
You're slowly but easy.
We then give the fibers a bath in a silicone mix like we used for the soft robot mold.
That does not smell great. It smells strong.
It's important to coat them as much as we can because
The silicon helps ensure that when we add the heat via the current that we pass through it, that the coils expand and then compress the entire length of the fiber, and that's how we get our motion of the fiber.
Oh, okay. So this is what kind of ensures the movement.
That's correct.
Okay. It is really hard to dip in here. Messy.
Very messy. Very
It's
messy.
not a clean process. It's a very manual, messy process.
after clamping down one side to hold it steady, we attach the other end to a drill to wind the separate fibers together. Doing this builds stronger muscles.
So should I start it?
Yep, go ahead. You can start.
Now I'm scared.
It's all right. Yep, okay. Okay, slow down. And you can see...
Oh, darn it.
Yeah, we were right there. We were right there.
If you missed it, we over-twisted and the strands broke. No big deal, it happens, and we can just start again. I guess just like us humans, building muscles requires patience, determination, and skill.
Good speed?
It's great speed. So now the strands are twisted together. The next they'll start doubling up and coiling. Building carbon fiber muscles or any type of artificial muscle is an art.
Oh my God.
There we go. It's really coiling there. Great. We'll stop there.
Great.
Now we're going to put it on a drying rack and put it in an oven and have it dry overnight.
Okay, cool.
And now it's time to put our muscle in the gripper we made.
I see it, yeah, it's totally opening. So what's the end goal of all this, right? We designed muscles, we made a gripper, we're using them together so that this gripper moves. What's the end goal?
The one that we're planning for, we would have it in a gripper unit that would sit on an end of a traditional robot. And so we're taking the benefits of the traditional hard-linked robot and the soft robot together to be able to allow us to manufacture things in space more effectively.
A bright future ahead, thanks to people like Jim. And the next generation. Jim says all the soft robots you see here were made by students.
We actually take students from high school level all through PhD. Working with them is fantastic. They really bring in great, different, novel approaches to solving some of these really hard problems.
And who knows, maybe the problems we solve for space improve the soft robots we use on Earth. And in that way, NASA continues to explore for the benefit of all.
Well, Jim, thanks so much for having us here. It was really cool to see how soft robots are being developed and built here at NASA, and I can't wait to see them used in space.
Absolutely. Thank you for coming. We hope you come back soon.
Whether it's traveling through deep space or staying nearby in Earth's orbit, a spacecraft needs fuel to propel it and the sun to power it. But what if I told you NASA is looking to use the sun for both power and propulsion? Another team at Langley is working on this bright idea, which could offer a new guiding light in exploration.
Oh, fancy meeting you here. Nice to see you.
Greg.
Thank you so much for having us.
Greg Dean is the lead assembly, integration, and test engineer for the Advanced Composite Solar Sail System, or ACS-3. That sail system is what we're now standing in the middle of.
And so this is a solar sail.
This is a solar sail, yep.
So can you tell me about it?
So a solar sail is effectively a propulsion system that doesn't actually have its own fuel.
Okay.
It uses sunlight. And so sunlight will reflect off of these big aluminized membranes. As light bounces off of it, it imparts momentum to the sail. And so light actually pushes it, makes it accelerate.
Whoa, so essentially you guys are sailing on sunlight.
Yep.
That's amazing.
Pausing to reiterate that Sailing on Sunlight is not your dad's favorite soft rock album. It's how NASA is trying to make getting to and traveling through space cheaper. The smaller and lighter a spacecraft is at launch, the better. It means a smaller, cheaper rocket to get it into space.
The goal is to make it as big as we can, but as light as we can.
Greg and the Langley team, along with NASA's Ames Research Center in California, spent 5 years designing and building this solar sail system. It launched in April 2024 from New Zealand, and now here it is, successfully deployed in low Earth orbit. It measures 30 feet by 30 feet, but future solar sails could be much larger. Think the size of a basketball court, or even bigger. Either way, the system will need to fold down as much as possible into a box the size of a microwave.
So this is the boom, these are the sails, these booms deploy the sails?
Yep.
Okay.
Yep, the booms deploy outward and it drags the sail with it. We have the solar panels here.
Okay.
Okay, and then if you look down underneath, this black part from about here to here,
Right?
that is the spacecraft bus itself. From there downward is what we call the sail boom subsystem. And that's where all of this packs into. So all of this actually fits in half of this box.
How does all of this pack into that?
Very carefully.
And it all begins with folding. And since I've folded my share of laundry, origami, bad poker hands, I thought folding what looks like aluminum foil would be a breeze. I was really wrong.
This one is absolutely thick, can crease, can hold shape. This doesn't hold shape at all.
No, it doesn't. It's too thin.
Is it okay that I do this?
Yeah, hold it up.
And so it just doesn't hold shape.
Yep.
What is this material?
So this is made out of what's called polyethylene naphthalate, or PEN.
That's so much easier.
So all it is a polymerized plastic, similar to like a Mylar party balloon.
Okay,
It's just very, very thin. It's 1/50th of a hair on your head.
1/50th
1/50th.
of a strand of hair.
Yep. It's so thin that honestly, if it wasn't metallized, you probably wouldn't even see it.
Okay, so listen, my mind was just blown. I think now we need to put one of those mind-blown emojis on the screen here.
I'm beginning to think this will be more like folding a fitted sheet. Impossible, but we're gonna give it a shot. And we'll do that inside this special enclosed area where we assemble the sails.
All right, let's fold this thing.
So just like when you buy a new piece of electronics, we got to peel off the wrapper.
Can I peel it off from this side?
Absolutely can.
Okay. Oh, I thought I ripped it. I had a mini heart attack.
So what we're going to want to do is pick this up and bring it into our track right here.
Okay.
And then important thing to point out is it does like to try to roll on itself, so we'll
Okay,
just
I
try
saw
to prevent
already.
that.
Yeah. It is really hard to move this with gloves on because the gloves prevent you from feeling it, and it's already so thin, so it's like you're
Yep.
not touching anything.
Now that you've laid down your first layer,
Okay.
we have these strips of paper.
Right, gotcha.
So what we're gonna do is we're gonna lay this down in here,
Yeah.
and then we're gonna Z-fold this, so we'll bring this entire edge back to us.
Okay. So does this have to be perfect?
No. For what we're doing
us.
today.
Yeah,
no.
yeah. No, but I mean for like when it flies, right? So already this edge is starting to curl.
It's kind of a spectrum, let's say.
Okay.
It does need to be good enough.
Okay.
But you know, that's sort of relative because it doesn't hold a crease.
That's why Greg says it takes one person, one work week to fold one quadrant. So that's a month to fold an entire sail.
This is making me like never want to fold anything ever again. Ta-da!
There you go.
All right, I hope we did okay.
Next up, we'll need to roll the sail around a spool.
I'll pull the paper. What you essentially want to do is with your left hand, you're gonna turn this.
Okay.
And then with your right hand,
Keep
you're
it
gonna
flat.
pull this nice and tight against it. Because again, so this is a real size spool for the spacecraft, right? So
Okay.
if your quadrant doesn't fit on that at the end of this, it's not gonna go in the vehicle.
I held my breath, afraid to rip the sail, which made me wonder what happens if the sail rips in space? I mean, there's a lot floating around the Earth, from micrometeorites to space debris. Greg says they thought about that too, so built rip stops into each of the quadrants by taking Kevlar thread and gluing it down in a grid pattern. That way, if something were to rip the sail, the tear would stop at the next Kevlar thread.
So you lose like a section of your sail,
Sure.
not the entire quadrant.
Hey, look at that! I'm so proud of ourselves.
There you go.
Remember, this is only one of 4 sail quadrants. If this were the real thing, we'd spool 3 more. Next step in the process, rolling up the booms. Think of each like a tape measure, rigid, but you can roll it up. When unrolled, it becomes rigid again.
Your job here is basically you're gonna have one hand on top
Okay.
to help that transition from mostly flat to completely flat.
Okay.
And you're gonna have another hand here just to help support it and compress it against this spool.
Okay. This is kind of like what we just did with the sail.
Pretty similar, yeah.
Okay.
And now, with the click of a button,
Am I doing okay?
Yeah, you're doing great.
Sounds like popcorn.
A little bit.
How do I know if I'm flattening it out enough?
The ultimate test here is does it fit on this spool by the time we're done?
Okay.
the boom is made of carbon fiber, which, just like the sail, is also super light. In fact, the full boom for each sail quadrant is 23.5 feet long, and yet that whole thing only weighs 1/3 of a pound. It's not only light, but strong, and resists changing shape. We do not want our booms changing shape as they experience dramatic temperature swings, going from shadow to sunlight several times a day.
Ugh.
And we're gonna stop there.
Perfect timing.
There we go. See, and so it's a lot faster because we motorized it.
Right.
It used to take a long time to do that by hand.
Right.
And we would damage things.
None of what we did today is flying into space.
You wouldn't actually let me touch flight material.
Oh, you know, I might.
Would you still have a job after?
That's a good question.
We secure it, and now, boom, done. Okay, we're ready for the final step in this process, and for that, we have to take this spool to that table.
Oh, that table.
Yeah.
I knew we'd get to it.
This is where we come to here, which we call the packaging table.
Okay.
And so
Really high-tech name there.
it is very descriptive.
Yes, very. So we have these wrapped up booms.
Mm-hmm.
And so I'm assuming this is this, essentially.
Yep. This is the same thing. We've just kind of pre-staged these ones.
Okay, gotcha.
So you have 4 full-length booms here.
Mm-hmm.
This right here is a prototype of the mechanism that's inside of the spacecraft that deploys the sail and booms. So the first thing we're going to do is unlock these arms.
Okay.
So you can go and pull that out for me.
Okay. And then there's another one here.
There's
Pull
one
out.
here and one here.
With the arms unlocked, time now to activate the motor and start pulling in the booms.
Here we go.
Oh, whoa. More popcorn.
More popcorn.
moving much more slowly than over there.
It does, yeah. So it moves slowly here because we typically have more people around monitoring everything and making sure that nothing bad happens.
That it's staying on the track?
Yeah, that it's staying in track.
So how long does this take to get all 4 into the one in the center?
If you're doing this realistically for flight, that can take close to an hour and a half.
Having this done on this table mechanically, that really cut back on the time?
Yeah, it cuts down on the manpower required to help us do this. You're not having to contain this. The table is basically doing all the work for you, and we're just here observing and making sure things are good.
Almost there.
Almost there. Okay, so we'll stop it right about here.
Okay.
Finally, we remove the arms.
I'm gonna take the center portion, and you're just gonna help me with the weight.
Okay.
Okay. And just careful, this arm isn't light.
Ooh, okay.
Okay.
It is not light.
We can go ahead and just put this down on the ground for now.
Maybe it seems heavier just because everything else we've been lifting today weighs nothing.
Now you can clearly see the ingenuity of this sail boom system.
How hard was it to engineer something like this?
5 years for ACS-3 on its own.
5 years on its own.
Yep.
So what's next for the real ACS-3? The one we told you is already in space, flying about 600 miles away from Earth. By the way, that's more than twice the altitude of the International Space Station.
It's kind of like you don't go on a road trip without making sure your tires are
Sure.
full or your gas tank's full.
Sure.
Same type of thing with spaceflight. So we have to go up and fly this and show that these things actually work in a real space environment.
Remember, this is a technology demonstration mission. What we learn from ACS-3 can be used to test a much larger sail in the future. It's a great start towards redefining deep space travel.
Well, I'm excited for you. I'm really impressed.
Thank you.
Congratulations.
Yes, congratulations to NASA Langley. Over 100 years ago, it faced a challenge that had never been solved, mastering human flight. Today, it faces new but similar challenges that center on the same core issue: exploration. Only this time, it's for deep space. They're advancing old ideas in clever ways, a robot that's soft and autonomous, and flight powered not by fuel, but by sunlight pushing a sail. It's this kind of ingenuity that NASA uses to carry us to the farthest reaches of our solar system.
We are at a different lab, and we're gonna make a muscle, if I can get this coat on.
All right, here we are. Demo, take 2. Terrible. So this is
I gotcha. All right, I do fit in a small. We'll show you how this solar sail could revolutionize space travel and how engineers at Langley plan to...
Absolutely. Thank you for coming. We hope you come back soon.
Just leave it at that.
Yeah.
Hope you come back soon.